So p hat is the one that you get from the data. Is that what you just said? Is that what you just said?
Sorry?
P hat is the number you get from the data. Like it's the percentage, well, the proportion of the individuals in your actual data that came up with your yes. Whereas P is the percentage of the people, all the individuals that could have happened coming up with a yes.
Oh.
Population, yep. So this is called a binomial distribution, and our big keeper of the distribution is a great big book of all the binomial distributions, and there's a different one for each sample size and each probability P. And it turns out that the binomial distribution looks like this if you do the probabilities. So if you turn these numbers into a graph, it tends to look like this, which looks approximately like a normal distribution. If you've got enough, if the probability of got enough individuals, it's close enough to a normal distribution to pretend that it is. And so when you take a normal distribution and you subtract its mean and you divide by its standard deviation, then you get the standard normal distribution. And so the binomial distribution, the mean is n times p. Because this is, if there's n people and p% of them say yes, then the total number that say yes is that percent of that number, which is why you multiply them together on average. And the standard deviation is the square root of n times p times q. That's the standard deviation of a binomial distribution. Oh yeah, that's what the q is. Because if this is 20%, this would be 80%, which is 100% minus, yeah. I say percentage, but I have to think of them as decimals. So if it's 20%, this is 0.2. So if this is 0.2, this would be 0.8 because that's the 80% and that's the 1 minus p. Depending on, yeah, I prefer 1 minus p, but the one I saw in the notes was a q. And if you take off, so whatever this x is, if you take off the mean and you divide by the standard deviation, you'll get a standard normal distribution, a z distribution, the one in the z table. Yeah. And even better, so this is whatever x is. Yep. Yep, I'm nearly there. This is what the distribution is. This is a calculation you can do based on the raw number of people who say yes. And this would be a standard normal. But if you wanted one based on the proportion of people that say yes, you calculated a percentage, then you do a slightly different calculation. So if this is a binomial distribution, but the thing you're actually calculating when you do this data is, where the hell is it? This. So P0, 1 minus P0, like that. Is that what you're thinking of? The P hat minus the...
Actually, there's an example in here with it.
Yep, let me have a look. Let's just do it. It's going to be easier to do it as examples because I'm tanking here, so I'm just going to go back to and do it. Here we go. The Laurier Company's brand market has a market share of 30%. In a survey, 1,000 customers were asked which brand they prefer. What is the probability that more than 32% of the respondents say they prefer Laurier brand? All right, I'm just going to analyze this. So there is a population of the consumers, which is, we don't know how big it is, but 30% of those consumers are Laurier customers. Okay, they prefer that brand. That's what this bit here says. That's telling me the value of P. So if I take an individual person, they will either prefer Laurier or they won't. Yep. And they've told us that 30% of customers prefer Laurier. That's the market share, which means that 70% don't. And that's telling me that the probability of picking a random person and then preferring Laurier would be 0.3, because that's the 30%. And the 1 minus P, which is the same as Q, is the 70% that's left. Okay, that's an individual person, and that's this first sentence tells me that information. If I pick an individual person, the chances of them preferring Laurier brand is 30%. Now we've said we've got 1,000 consumers and we're asked what brand they can prefer. And so now we've got like 1,000 people. I'm not going to draw 1,000 of them. 1,000 consumers. Yep. And every one of them either prefers Laurier or they don't, right? And so what I'm going to write down is how many of them prefer Laurier. Yep. The number that prefer. So what I've done is I've done this experiment 1,000 times. And what that means is that the number that prefer Laurier is a binomial distribution. Or not just the number that prefer Laurier, I could also calculate the percentage that prefer Laurier, right? Proportion. So normally you'd call this X and you'd call this P hat. And so this, that we've been told that this P hat is 32%. That's 0.32 because it has to be written as a decimal. How are we feeling so far about my interpretation of this question? Okay. Okay, I know. So this X would be 320, right? 320 people is 32% of the 1,000. Just, it's not important to the question. I'm just pointing out that those people are there. Okay. So if I wrote down all the possibilities for how many people in this 1,000 people would prefer Laurier, it could be anything from 0 to 1,000 people could do it. On average, it's going to be 320 because that's the proportion we'd expect. Sorry, just 300, sorry. On average, it's going to be 300 because 30% of them we'd expect. So we'd expect 30% of the 1,000, which is 300 people, to prefer Laurier. That's what we'd expect. That don't need this in your calculation, but that's just what I'm thinking about, right? So the number of people who prefer Laurier comes from a binomial distribution. Because that's what it is. I've done this Bernoulli trial 1,000 times. And when you do a Bernoulli trial any number of times and add up how many times the thing happens that you want, the yes, that's the binomial distribution. But I also know, and that binomial distribution has a mean and a standard deviation, and it's approximately normal as long as there's enough. Yep, that's how she's done it. Okay. And it's approximately normal. Okay, so this is a binomial distribution with trials 1,000 and probability of success 0.3. And so the mean is this thing here, 0.3 times 1,000, which is 300 people. That's what I would expect on average. The standard deviation is the square root . What I've said is true, it's just not what she did. The standard deviation is 1,000 times 0.3 times 0.7. So you do the P and the Q, multiply them together and times by 1,000, which is whatever it is. I don't know what that is. So a number. And I could use those to calculate my probability, because I'm going, well, it's a binomial distribution, which is nearly normal. Here's the center, which is 300. Here's my 320, and my probability of more than 32% would be this probability here. because these are all the things. But I'd really prefer, since my original question was about percentages, I'd really prefer it to be about percentages. So I'm just going to start this question again and go back to here and say P hat has approximately a normal distribution and the mean of P hat should be P, should be 30%. So on average, if 30% of people prefer Laurier, then on average in any group of them, 30%, the percentage should be 30% on average. And the standard deviation will be the square root of P times Q over N. Which is what calculators are for. Okay. So I want to know what is the probability that the specific proportion I get in my sample is more than 0.32. That's the question that I'm trying to figure out. And it's a normal approximately normal distribution with this mean and this standard deviation. So I should be able to subtract the mean and divide by the standard deviation. $14.49. Are you supposed to do them as decimals? Not as.
Oh, okay.
It's not 30 times 70. It's 0.3 times 0.7.
Oh, right.
You can actually do them as percentages, but then you have to make this not a 0.3 but a 30. So if this is as a decimal, then these have to be as decimals too. So if I subtract the mean and divide by the standard deviation, that will produce a normal distribution, a standard normal distribution. So this is the picture here that I started with. It has an average of 0.3, and here's my 0.32, and I want to know what this probability here is. And I know that the standard deviation, like how wide this is 0.01449. But if I subtract the mean and divide by the standard deviation, now the center is 0 and this width is 1, and this number is whatever this calculation here produces. 0.32 minus 0.3 divided by the answer I just got is 1.38. So this thing is called a Z, like that. How do you feel about what happens just here? This picture is what the options are for P hat and how likely they all are. And then I subtract the mean and divide by the standard deviation, and that produced a picture that is the options for what Z could be. And that I can look up in a table somewhere or ask Excel what that answer is. I don't have a table handy. No. Oh, wow. Oh, no, lost it. Where'd it go? I've lost the page that you were looking at, so you can find it, but it's all good. I don't know what your Z table looks like because they all come in different flavors. Different courses have different Z tables. This is it. All right. So read this carefully. It says the table values represent the area to the left of the z-score. My picture, I need the area to the right. So I could do that, but I could also know that the thing is completely symmetrical. So I could do the area to the left of minus 1.38, and that would be fine as well. So this is the same as the probability that area is less than minus 1.38 because a normal distribution is perfectly symmetrical on either side of 0. And that avoids me having to do 1 minus anything along the way. So here's minus 1.3 here. 130, 131, 132, 134, 135, 136, 137, 138. There, 0.08379. So my picture is the bit above, but the table only gives me bits below. And so what I'm going to do is I'm going to flip it round this way, flip it backwards, so that the table directly gives me the area below. I could have looked up this one and done 1 minus that, but this cuts down on one calculation that I could get wrong. So it's quicker that way. You're welcome. And so there's 1.3, and I go all the way along to the 0.8 column, which is here. And so it's 0.8379 is 0.08. So we have a roughly 8% chance of a group of 1,000 individuals having 32% preferring this brand or more. So not much. That makes sense. If you've got 1,000 people, then they're really going to be quite close to the average percentage of them that prefer this brand. So if I had less people, then this standard deviation would have been bigger because I would have divided by a smaller number. And then this would have been wider, which would meant this probability would have been higher. Yeah.
Basically, what we do is standard deviation, and then you do the z, and that's how.
Yep. So because of this distribution, that means that when we do a hypothesis test, we can do this calculation to figure out how likely my data is. And so then I'll go, here's the Z distribution. Here's my Z that I calculated from my sample. And then I would normally, if it was greater than, I would want this probability. If it was less than, I'd want this probability. And if it was not equal to, I'd want both of them together combined. Yeah. So if this, in that story that we just told, where there were, what? Okay. So in this story that we just told, suppose it was a different question entirely, and we had the same information, but now the Laurier company is now asking, do we believe that our market share really is 30%? Okay. So if that was the hypothesis test we're doing now, so is the market share 30%? That's the question. The null hypothesis would be that the true proportion is 30%. Yep. And the alternative, the way it's stated at the moment, it just says, is it 30%? And it hasn't given a preference of one way or the other. So that would be that it's not. And then, well, the calculation I've just done here is exactly the calculation you would do to do the hypothesis test. I got my p-hat from the data. So let's just pretend I got that 32% from my data and I had 1,000 people. Then the Z statistic would be the one I got from the data minus the one from the null hypothesis divided by P0, 1 minus P0 on N which is exactly the calculation I did. And that came out to 1.38. So my Z table told me that this area was 0.08, which means that this area is twice 0.008, which is actually quite large, 0.16-ish. I'd get a calculator to do it properly, but so I would then conclude, then I would ask myself, well, do I believe the null hypothesis or not? So if the null hypothesis, so if the percentage really was 30%, the chances of getting data getting a percentage further away from 30% than what I've got is very high. And so I conclude that I would not reject the null hypothesis and say, yep, I'm happy to believe that the market share really is 30%. Yeah, you got to pick a significance level, but no, they would do that for you. So, if you're not given a significance level, you just say a significance level. So I would say you pick 5%. Because that's what Fisher did when he first invented hypothesis tests. So we're going to do the same thing. So at the 5% level, does your lecturer use the word retain or just do not reject? Okay, do not reject H0 and conclude the market share could be 30% still. You should never be hard and fast. You don't conclude it is 30%. You conclude it could be. Yeah, there is no evidence to suggest that it's not 30%. Yep. Okay, that's the general vibe of how these things go. So what I've done here is that one question was not technically a hypothesis test. It was literally just about the possibilities for what could happen when you collect this data. But hypothesis tests are built on that idea. And that's one of the reasons why your lecturer has arranged the course the way they have, because that's how the ideas are built. Yeah. Yeah. So if my p hat had been much higher, then my p-value would have been much lower, and I might have rejected the possibility that the market share is 30%. Yeah. But ultimately, this one's really quite high. I wouldn't have rejected it for almost anything. So, yeah. All right. Yep. Mm-hmm. Okay, just a second. I'm just going to answer this one question. What's a low p-value? So what you have to do is you have to pick a significance level, and anything lower than that counts as a low p-value. So if my p-value had come out as 0.03, I would have considered that low because it's under 5% as a decimal. Does that answer the question? Yeah, cool. All right, I do want to finish one more thing. Back. The relationship ones. There are several situations you've been given about how that goes. So it's usually that every individual has both a situation and a number recorded on them. So they're either like, they prefer or they don't prefer Laurier, and the number is how much they spend, or you've used one mechanical process in the factory or another, and the number is how much the cereal boxes weigh, or you've used one strategy in your marketing campaign or another, and the number is how many sales there are. And so that's the normal situation. And every individual is in one situation or another. There's like two categories they could be in. That's a common situation here. And then your question is, does what situation you're in make a difference to the number? But the way it's pitched, like in this situation A and situation B, the way it's pitched in this course and the way it's pitched in order to make the maths work out to help you figure it out, is that you say, all right, well, there's a mean in situation A, and there's a mean in situation B as well. And this is a mean number 1 and mean number 2. And if what situation you're in doesn't make a difference to the number that comes out, then these two means should be equal. Because then the situation doesn't make a difference. And then what you normally pitch that as is mu1 minus mu2 being 0. Because then you've pitched it about being a single number. This is the single number, the difference between mu1 and mu2, and it's equal to this particular answer. And that's where you go. This thing. And you do that t-test. This is the two sample means minus the difference between the two population means, and this is the standard error. But there's all these different stories, right? There's one where you know both of the both of the population standard deviations. There's one where you don't know the population standard deviations, but you're pretty sure that you believe that they're equal. And there's one where you don't know the population standard deviations, but you don't believe they're equal. Yep. The rule I was taught is that for you to believe they're not equal, one of them has to be at least twice the other one. Yeah. So if one of them, when you did 1 divided by the other and you got 1.5, you'd go, that's equal enough, usually. And that in itself is also a hypothesis test, because you're using the critical value of 2 to make your decision of are they equal or are they not. So if you do more stats courses, you'll learn how that works. Also due to Fisher. He invented most of modern statistics. Well, most of modern statistics up to the advent of computers. This isn't mine, this belongs to one of the students, so I can't share that, I'm sorry. Yeah. I would recommend to you organizing your hypothesis tests in a way that makes sense to you for making the decision. A lot of people like doing it as a flow chart. Is everything okay? Excuse me. The thing. Okay, that's enough. I've had enough of that. Right. So, I just do want to do one more hypothesis testy sort of thing, which is just give me a moment to get it. This thing. You guys in the Zoom can't see it. Sorry, just a second. Okay. So this says The relationship between expenditure on ambulatory care in dollars and age in years is given by the least squares regression estimated using this data with a sample size of 2,450. I presume this is in one of the assignments. So I hope they're not planning to reuse it. And it says ambulatory expenditure is equal to this number minus 82.761 plus 41.932 times age. And these things in brackets, I reckon, are the standard errors. So standard errors. Okay, so this problem is about the relationship between these two numerical variables. And the ultimate question here is, how are they related? Which isn't either of those questions I had before. The ones I had before are what are this number and yes or no question. There's a bigger question you can ask, which is how are these things related? And really, which is what's the formula? If I wanted to answer the question of are they related, I could ask myself whether this number ought to be 0. Because if that number is 0, then ambulatory expenditure is always the same answer. Because what age it is doesn't make a difference. Yeah. Anyway, this is the situation we're in. So based on the regression results, how much does ambulatory expenditure change as age is increased by 1 year? So if I had an age of, say, 20, it would come out to a certain answer. And if I went up to 21, I would get an extra 41.932. And that's the idea behind it. Every time there's an extra 1, it goes up by that number. Yep. They are the standard errors, which means, let me just talk about that. You need it for part B and part C. Yeah. So I'm just going to write this thing down. Okay. I'm just going to stop sharing that. Thank you. So these numbers are called standard errors. And what standard error means is it's a reference to the distribution. So if I imagine all the data that could have been, and all those data would produce different numbers when I did the regression. So if I imagine all of the slopes that could have been, this is their standard deviation. So this thing is called beta 1 hat, right? Beta 0 hat, and this is beta 1 hat. I think that's what your lecturer calls them. What do they call them? Little b. Okay. Those numbers, what we're saying is approximately the distribution of all the possible beta 1 hats has a standard deviation of 4.464 or whatever it is. Let me just look it up. Yeah. Okay. So, cool. So at the moment, my question A was, how much does a change of 1 year in age make a difference to the ambulatory expenditure? So I know that one more year in age increases ambulatory expenditure by $41.932 on average. Okay. It's important to use the word on average. Otherwise, because it doesn't actually, if you have two people who are different in 1 year, they're not going to be different by exactly 41.932. That's just an average difference. It's all averages. Because your scatter plot, right? goes like this, and two people who are 1 year apart, this person and this person, they're all going to be different distance apart, but the average difference is this. That's the idea behind it. And that's the slope of the line of best fit as well. I know it's an increase because this is a plus. If this was a minus, it would be a decrease. How do we feel about the answer to that question? So there's a sentence you have to say, basically, and you put the right things in the right spots. This is not English, this is maths. You don't have to say things in your own words. Let's say question B said, give a 95% confidence interval for the population slope. Okay, so we know that the sample slope is the beta 1 hat, which is this number here. 41.932. That's the sample slope. The number that is multiplied by the variable. And we want a confidence interval. So we're saying, well, this is the one that came in our sample. What am I happy to believe what the slope is for the real population of all possible individuals I could possibly have asked or ever ask. And that is the population slope. Okay. So I know that this is I'm going to do part C first, if that's okay. I'll come back to that. So part C says, using a significance level of 5%, test the hypothesis that the slope parameter equals 42.5. Okay. So they explicitly said equals, and they didn't say anything about more or less. So this is my alternative hypothesis is that it's not equal. I don't know why we care. It's actually usually traditional to test to see if it's 0. Because if it was 0, there wouldn't be any relationship. And so you would know it's relationship. But I can test it compared to this. And this is a t-test as well, because the answer comes out to a t. So what our good friends in the 1890s to 1930s discovered was this: if you take the beta hat and you take off the null hypothesis value of beta 1 hat, of beta 1, and divide by the standard error of the beta 1 hat, then it should be a t distribution. And so that's my beta 1 hat minus. So my beta 1 hat in the data was 41.932. And I'm comparing to 49.25, and the standard deviation, the standard error was 4.464. And then when I do that calculation, it comes out to whatever it comes out to. $41.932. Not doing well. So this comes out as 0.1, like that. Right, this is not going to be significant. Like this p-value is going to be more than 0.05. I can tell right now. Your t-distribution normally has to get beyond 2 in order to give you a p-value under 0.05. But I'll do it properly. So here is my diagram of all the values that t could have been. With 0 in the middle. Here's mine, a minus 0.127. And there's the probability below, and there's the matching probability above on the other side. So basically, I'm saying I'd be just as surprised if it was 42.5 as if it was the same distance below. Just as surprised at being 41.9 as if it was 42.8. Yeah, something like that. Yep.
So normally we try to find the t table.
Yep, this would need to be in a t table. That's okay, because the t table is perfectly symmetrical. Have you got a t-table there on the screen? Can I have a look at it? Now, just need to say, it has to come from a t-distribution with n-2 degrees of freedom, not n-1, because this is a whole different situation. So this is a n-2, which is t, how many did they say I had? 2,450. Okay, so 2,448. Oh, well, that's not important. Okay. So this is a t-table. Ah, damn it. Let me just stop. No. This is a t-table here. Okay. This is different to the way the normal table works. Because there's a different t for every number of degrees of freedom, they can't give you the whole amount of all the possible values that t could be. They only give you the values of t that give you specific probabilities. So I need to go down to row 2,448, which isn't in my table. So I'll just use the next available row, which is the infinity row. That's what I do. Is that okay? So if I had gotten my t to be, t26, I would use this row, and t30, I would use this row, and t500, I would use the 1,000 row because that's the next one, and anything above 1,000, I'll just use this row. See how it says Z there? Z is the infinity t distribution. So, okay, so I'm looking for the t that goes with the 5% significance level. And I'm using both tails because it was a two-sided hypothesis. So I'm using both tails. And so this is automatically giving me the outside of the thing. So when I go down to this row and I want the 5% mark, which is here, it's 1.645. So what that's telling me is if I had gotten a t of plus or possibly minus 1.645, then that area there would have been exactly 5%. That's what this table here says. So this table here says that to get exactly 0.05 with my, oh damn it, wrong one, two tails of 0.05 is 1.96. So if my t statistic had come out to be exactly 1.96 or minus 1.96, I would have gotten exactly a p-value of 0.05. My area is way bigger than that. This area here is much bigger than that. In fact, if you look here, my number is minus 0.127. So let me look for, it doesn't matter whether plus or minus, 0.127 is between here and here. And so 0.127, the p-value is somewhere between 0.5 and 1. If my number had been, 1.38, the p-value that was between these two, and the p-value would have been between 0.2 and 0.1. How do you feel about how I'm using this table? Okay. So this is the critical value of t, I call it. But I'm going to say, so the p-value is definitely more than 0.05 because it would have to be, this would have to be all the way up to 1.96 in order for the p-value to be exactly 0.05, and it's much further in than that. And so therefore I do not reject. And I conclude that the true slope could be 42.5. All right, that's the hypothesis test. You can have this back now. Okay, so the next question was using so the previous question was find a 95% confidence interval for the population slope. Okay. I know that this is what my current sample gave as a slope, but the population slope is probably not exactly equal to that. And so I'm going to give a range of possibilities. confidence intervals, which I haven't covered yet, but this is the general idea. Confidence intervals go with hypothesis tests. So a confidence interval about a number is very closely related to a hypothesis test about a number. My question here is the number equal to this number here? This is what is the number? So if I had, the confidence interval contains every number that I would have been happy to believe based on a hypothesis test. So I know that 42.5 is fine because I accepted that, I didn't reject it as my H naught. And I also know that 41.5 would be fine. Sorry. I also know that 41.9 would be fine because it's the same as this. So the one I got in my data, I'm totally happy to believe as the population one. And there's all these other numbers that I would have been happy to believe based on a hypothesis test. And all of them together, they are the confidence interval. And outside that, there are ones that I'm not happy to believe because they're too far away from what my data is saying. So this one here, gave me a p-value of like 0.6 or something. And then some of them would give you p-value of 0.10, and that I wouldn't reject that. Some of them give me p-value of 0.06, I wouldn't reject that. This one I would reject, it give me a p-value of like 0.03. And right on the very edge is one that would give me a p-value of 0.05. Exactly. And that's the point at which I would stop believing it if the p-value got below 0.05. And there's another one over here too. So I need to figure out what values that could go in this spot that would make this t work out to be further out, like further in than the 1.96. And so to figure out the exact edge, I put 1.96 in this spot and rearrange the algebra. That's how they're connected to each other. And it works out like this. The value of beta 1 that I'm happy to believe. So 95%, damn it. 95% confidence interval endpoints are that beta 1 is the beta 1 I calculated up a bit and or down, up a bit and down a bit, some number t, which I call t star. I don't know how your lecturer writes it in their formulas. Oh no, they do like t alpha on 2. Cool, that's fine. That's what your lecturer calls it. Times the standard error for beta 1 hat. That's because these pieces are all in the hypothesis test as well. That's the beta 1 there. There's the beta 1 hat. There's the standard error, and there's the t. And they're in a different order because I'm calculating a different thing. And doing this calculation will produce the endpoints you want. And this t alpha on 2, what that means is it's the correct t that would have given you a p-value of exactly 0.05. And so when I look that up in my table, the two-tailed t value that gives me exactly 0.05 is 1.96. And so my beta 1 lower end is the 41.932 plus or minus the 1.96 times the standard error, which was 4.464. So I have to do the calculation with the plus, and that'll be the top end, and the calculation with the minus, and that'll be the bottom end. Doing okay? Yep. I would imagine in your course you would be given the standard errors because the computer has to figure that out using all its fabulous formulas with the SSTs and the SSEs and the stuff. All right, well then maybe they'll give you the SSTs and the SSEs and whatever. I would not expect your lecturer, though I don't know what to expect, to give you a set of data and ask you to calculate them. I wouldn't expect that. But they could give you an Excel output with the SS's in it and the missing values for what the standard errors and stuff is, and then you would have to calculate them yourself from the bits. Does that? Yeah. that's a classic stats lecturer thing to do. Yeah. So whatever this is gives me two numbers. One's a bit more than 41.9 and the other one's a bit less. But I don't know if I can bother calculating them. So you'll be one with the plus and one with the minus, and those two numbers will be the confidence interval. And you put them in brackets. Your lecturer apparently uses square brackets. Good-o. That's fine too. Oh, really? Cool.
Yeah, so I don't think I'm not sure.
I mean, it's similar to the formulas for other confidence intervals like this.
Yeah.
And it's just the same vibe as those formulas. So it's the same deal. And for me, I find it easier to know the bits that are in the t-test and then rearrange that to get the confidence interval. I know that the shape that confidence intervals are, and they've got the same pieces because they're using the same data to answer different questions. Right. Cool. So actually, I really do want to do this. I'm actually going to calculate these numbers. So 41.932. Come on, minus 1.96 times 4.464. And this is 32.56. And if I do that with a plus instead, I get 50.075. Okay. So now that I've done this, I want to tell you a different way of answering part C. The confidence interval contains all the numbers that would go in this spot in the hypothesis test and not reject. So if I've got a hypothesis test which says the beta 1 is 42.5, I know this confidence interval contains all the numbers that I would put in this spot and not reject them with a two-sided 5% significance level. Since this number is inside that zone, I'm not going to reject it. So I can say, I do not reject since 42.5 is in the 95% confidence interval. I'm allowed to do that. Yeah. You've got multiple choice, so you don't have to show work. I don't know if your lecturer would like this working, but it's totally true. That's how confidence intervals and hypothesis tests are related to each other. Yep. I mean, I don't know. If you haven't been given instructions that say you have to upload working, then right. If it is multiple choice, you won't be showing working as far as I know.
Well, this one quite basically we have an answer booklet that answer for page, but what's in this section page for one.
Is it online or is it? Oh, okay. I don't know then. If it's a face-to-face exam, then some multiple choice exams do a thing where you choose the multiple choice answer. And if you don't show any working, then you get 0. But if you do show some working, then you get the mark if you get it right. And if you don't get it right, but you show working, you get like half the marks. But I don't know. The rules are that she has to have given you this information already.
Isn't the rule she has to be available before exams?
I believe so. But they have to tell you the information about how the exam is going to work. Okay. Okay.
Oh, she didn't say she was.
All right, it's got to be in my uni somewhere. And if it's not, then you need to contact the head of school and say, it's not there. Can you please tell Virginia to do her job? But maybe not in those words. It's on the recording now. Oh, well. Okay. Tell whoever the lecturer is this semester to do their job properly. Okay. Right. So I know that if I had done a hypothesis test with the number 60 in this spot, I would guarantee to be rejecting it because it's outside the confidence interval. But that only works for two-sided hypothesis tests because the confidence interval has two sides. So it's only going to work for two-sided hypothesis tests. So just be careful on that. Yep. Don't know. Is she one of the tutors?
Yeah, she's another
tutor. Okay. Never met her. Yeah, she's probably one of the tutors. But you could always ask that person because then they might have a better chance of actually talking to the person who knows. So, okay. When is the exam anyway?
next Tuesday.
Right. Okay. Okay. So, how are you feeling about that sort of thing? Like what I did in that working. Okay. All right. All right. One day I'll do a really good seminar for data analytics. And then the next year they'll change the course and it won't apply anymore. I'm hoping I'm doing all right. Okay. So you asked about independent and stuff.
Yeah. You start the question there.
I'm just going to run with this.
Yes. Yeah.
Oh, yes, that one. I forgot that one. All right. So a statistician, possibly a statistics lecturer, classifies his students according to their gender. Of course he does. Sorry. It's 2021, people. You don't need questions that involve gender. But anyway, according to their gender and the hours of work that they do a week, the following table gives a proportion of students falling into the various categories. One student is selected at random. Given that the student selected is female, what is the probability that they work between 1 and 8 hours a week? Okay. Cool. All right. So okay, 0.06, 0.12, 0.2. And presumably they all add up to 100%, we hope, because that would make that would be important. Okay, so just guessing, like in our collection of students, 20% of all the students are both male and work for 1 to 8 hours a week. That's what this table is telling me. Okay, so we're being asked that the probability that they work for 1 to 8 hours, given that they are female. Does this notation look familiar to you? Okay. So the grammar of this sentence asked for the probability that she works for 1 to 8 hours a week, which means that the 1 to 8 hours a week has to be next to the P. And that was given that they're female, which means that's after the here. Probability problems are at least a quarter grammar. Okay, so this to me would say that we would need to be looking at just the female students and say, what's the probability of being here out of all of this? So this should be the probability of 1 to 8 hours and being female. Does your lecturer use this symbol for and? Or do they just use, okay, cool. And being female out of the total probability of being female. But just in terms of the picture, these are all the female students, and out of those, 18 of them are whatever. So this would be 0.18, and then there's 0.12 and 0.18 and 0.2 and 0.03. So whatever that works out to be is the probability. So this is the intersection of these two things. There's the 1 to 8s, and there's the females, and the intersection of those two things is this. So that's why it's this symbol. So 0.12. Exactly a third. So 1/3 of the female students work 1 to 8. Not that female is a gender, but anyway, it's a sex and they're different things. Anyway, not going to get into that. Yeah. All right. So, is it 0.53? So you've got 12 and 18 and 20 and 3, which adds to 54 according to my calculator. That's 20, that's 30. Oh yeah. What did I wrote 21, not 20. All right, so slightly more than a third then. All right, cool. Well done. When I actually typed it into my calculator, I didn't write 20, I wrote 21. It's a small phone and I've got big fingers. So, okay. So, cool. If this was different to the probability of being female, of having 1 to 8, then these two events of being female and having 1 to 8 would be not independent. So just to make sure I've got it, the probability of just 1 to 8 hours is 0.2 plus 0.18, which is 0.38, which is not the same. And so therefore the event of being female and the event of working from 1 to 8 hours are not independent, because knowing about one, when I don't know whether they're female, this is the probability of working 1 to 8. But when I do know whether they're female, this is the probability of working 1 to 8, and they're different. So they're not independent, those events. Independent means that one of them doesn't affect the probability of the other. And you can only tell if things are independent by doing a probability calculation. Mutually exclusive means that they can't happen at the same time. So these events are definitely not mutually exclusive because they can happen at the same time. There's 18% of people have both of them at the same time. So I know that they sound similar from an English point of view. Independent sounds like not having anything to do with each other. Mutually exclusive means, well, you know, they don't overlap, but they are used in completely different senses. So independent, the picture for mutually exclusive goes like this. You've probably seen it before for a Venn diagram. The picture for independent is much harder to describe. So if I just have, I'm just going to cut this into pieces. If I had an event that happened a quarter of the time, it would be this size. and an event that happened, an event that happened like half the time might be this. This is a Venn diagram using squares instead of circles. These are mutually exclusive because they don't quite overlap, right? These ones do overlap, and they're independent because this one happens half the time, and out of just this bit, it's also half the time. So they overlap in just the right exact way. That's what independent means. Whereas if they were like this, did a really bad job there. And this one was here instead, it overlaps the big thing half the time, but it only overlaps the bottom thing a quarter of the time, overlaps this bit a quarter of the time. So since those are different sizes relative to the thing they overlap, they're not independent. So you can't tell from a Venn diagram whether they're independent, you can, unless you actually calculate the areas involved. That's the difference. Yeah. But just one thing to know, independent events have to be able to happen together. Because if things don't happen together, then you know one of them, then the probability of the other changes to 0. And so it tells you everything you need to know about the other one when one of them happens or doesn't happen. Yeah. All right, what's the other problem? Yep, okay, let's do it. Last question, and then I'll stop. A random sample of some number. Oh, I actually wrote that down earlier, didn't I? And I probably just lost it. Anyway, random sample is 64, I believe, probably. It's under the shine, but I think it's 64 observations. Has a mean of 30. So that mean is from the sample, so that means it's an X bar. The population variance is assumed to be 9. So sigma squared. So sigma squared is 9. And 85.3% confidence interval. What the actual frell? Population mean. Okay, cool. I'll forget to give it back to you if I don't do this. Okay, so here is a situation where we have, so we've got a whole lot of individuals, there's 64 of them, and these objects, we've measured the number on each of them. So if I was going to do a hypothesis test about the population mean, I would do a t-test in this situation. No, I would not, because I know the real standard deviation. So I would do a z-test. So this is what I'm thinking in my head here. A hypothesis test would be a z-test. And what I would do in that hypothesis test is I would take the sample mean, I would have the sample mean, I'd remove the null hypothesis mean, and I would divide by the sigma on root n. That's what I would normally do. All those pieces are going to be part of the confidence interval as well. So the confidence interval, the endpoints of the confidence interval will be mu, and it'll be the x bar plus or minus the correct value of z times sigma on root n. Yep. Sweet. And so we know what this number is, it's 30. And we know what this number is, it's 3, because it's the square root of 9. Yeah, because the sigma squared is 9, so the sigma is 3. And we know what n is, it's 64, so this will be on root 64. And I'm still going to need to have a z. Do you have that z table handy? Reckon you can get that z table?
Oh, the Z table, yeah.
So I need to choose the z so that I have 85.3% confidence. Thank you. All right, here we go. So confidence goes with, right, confidence goes with the p-value. So this is my z. 95% confidence goes with a p-value of 5% on the outside. So I need this bit in here to be 85.3%. That's what I need for this z to make this 85.3%. Which means the bit on the outside, these two together must be 100% minus 85.3%. Which is, well, if we took off 85, we'd get 15, and then we have to take off 147. Yeah. And so just one of them must be divided by 2. So if I find that value in the Z table, 0735, that's about there-ish. So I've got 0743 and 0700, it's somewhere in between these two. So minus 2.1. Oh no, that's an O, sorry, wrong. I was looking at, there's a 17, 0735. 07, there it is, right there, 0735. And so it's minus 1.401234.5. It's 1.45 according to the table. And so therefore the confidence interval would be, the ends of the confidence interval would be 30 plus or minus 1.45 times 3 over root 64. Now you notice what I actually did, I looked up this one, but it doesn't matter whether I use the positive one or the negative one because it's symmetrical. Which is whatever it is, there's two ends. Thank you for being here. I hope that it was helpful to you. I'm going to stop the recording there.